Okay, this is the second hour of Physics 1C for December 1st, and what we're going to talk about now is understanding the curl from a geometric perspective. So let's get on to that. For this, we're going to need to draw another figure. This is a little simpler. I'm going to go down a little farther, but I can't go. Maybe when I start drawing, it'll go down. All right, so let's start off with, I guess we technically need a three-dimensional thing here. So let's start off with an XYZ plane. Make it black, make it just a little smaller, and then here we don't need most of this actually. We don't need. Oh, please let me do this with the. It's not going to let me though, is it? No, I have to pick up the thing. All right. It's just a lot easier to do a lot of the drawings with a mouse than it is to do with the pointer, but that's fine. Okay, so we want to erase that piece of it. We really don't even need the part that goes in the negative direction here either. So that way we can kind of use more of our picture. Look at that, okay, now it's disconnected, but we can still select it all and change the size if we want to. That's probably too big. Oh, that's good. Really don't even need this other thing going way back in the distance, but we'll keep it there. All right, so we've got a XYZ coordinate system again. This is going to be the X direction down here. This is going to be the Y direction. That's going to be positive Z up there. And we want to understand how we're going to find curl. And in order to do that, and looking at this is going to bother me. We're going to need to get rid of this too. It's just going to get distracting. Okay, there we go. What we're going to do is we're going to look at kind of like a box in the XYZ plane. And our box is going to have side lengths similar to what we had in the last problem. This side is going to have a length dx. This side is going to have a length dy. And what we're going to do is we're going to kind of look at finding the z component of the curl. So our kind of, well, that's not the way of putting it, I should say. We're going to look at doing kind of a sum of our vector field. In this case, we'll use the magnetic field. Dot product with dl. So we're going to sum up this kind of quantity here. So going along each side of this path right here, this rectangle, we're going to evaluate what that's equal to. Kind of like, if you look at this, it pretty clearly looks like we're doing a line integral. And that's effectively what we're doing here. But we're only doing it at this one plane right here. So in order to do this, we're going to need to know the value of this field, B. It doesn't have to be a magnetic field, but I'm going to use the word magnetic field because that's what we've been using in this class, on each of these sides. And so we're going to say that the magnetic field on the left-hand side over here, we're just going to say, let's let it point this way. It could point up or down. It doesn't have to necessarily point up, but this is going to be the y component. We'll call this one by. And then over here on the right-hand side, we'll have a different value that we're going to call by prime. And then on the top, we'll have, or we'll start in the bottom. On the bottom down here, we'll have the value of the x component of the magnetic field that we'll call bx. And on the top, we'll have the value of the x component of the magnetic field on the top half. So this one we'll call by prime. All right, they have these lengths associated with their sizes, and the arrow tells you if it's positive or negative, basically. All right, so we want to evaluate this quantity. We want to take the sum of b dot dl around all four sides of our thing. Okay, let's move this a little bit. So the dl's, by the way, are going to be pointing, we'll do this clockwise. So on the bottom side, dl will go this way. On the top side, dl is going to go this way. And we're going clockwise, so over here, dl is this way. And this is just a line element associated with our loop, and over here, it's going to be this way. And the direction is going to matter because if they're in opposite directions, you're going to get a negative sign. If they're in the same directions, like on the bottom, you'll get a positive sign. So let us start on the bottom side. The length of the side is dx. The vector is bx. Bx and dl are in the same direction. So on the bottom, we're going to get bx dx. This is the bottom. Plus, we need to do the one on the right-hand side. This one's going to be by prime dy. The next one's going to be negative. The next two will be negative. On the top side, we're going to get bx prime. Bx prime is going to the right, and dl is going to the left, so then we're going to get a negative sign out of that. So we'll get bx prime dx, because the length of the side here is dx. And then on the left-hand side, we'll get negative by dy. There we go. No vector symbols on the right because we're doing a dot product, so we have nothing but scalars left. If we group terms here, let's go back to black. Here, this was bottom, right, top, left. Should have continued writing that. Okay, so if you kind of group some terms here, like if we group the bx, dx, and the bx prime, we get something kind of similar to what we got before, which was this bx minus bx prime times dx. And then what we also have plus, the other one's inverted, so it's by prime minus by times dy. Similar to what we got before. In the last part, we had this ex minus ex prime that showed up, right? Right there. Similar kind of thing happening here. So again, what we're going to do is we're going to come up with an expression for that bx prime. I kind of want all this to be in black. It's just because this is all part of the same derivation here. All right, so what we need to do is we need to get an expression for what this is, for what bx prime and what by prime are. And similar to what we did before, we can say that the following should be true. The value of bx prime should be equal to the value of bx, which is the value down here, plus whatever the rate of change is. I'm going to leave that as a kind of open thing here, multiplied by the change in the direction that we're going. And bx and bx prime are now separated by dy, right? We're going from this point to this point here. So if I want to know the value of bx prime, then I need to know the value of bx plus the rate at which it changes in this direction times dy. So what that's going to be in the numerator here then is going to be the rate of change of the function, which is bx, with respect to, can you guys guess what I'm going to put on the bottom? Yeah, you want to think it's dx, right, Mr. Meowers? You want to think it's dx. But dx is left to right direction, right? And we're going up. So if I want to know, so I think it's, if you think about this in terms of points, it might be a little bit easier. It's a vector field, so at every point you've got 3 numbers that describe it, right? But we're going from, like, we'll call this like y1 up to some other point over here, which is y2, right? And presumably, bx is in general some function of x, y, and z. This might be kind of weird, but individually, the x, y, and z components of the magnetic field can be a function of x, y, and z, right? Like, you could have a magnetic field that looks something like this. It could be something like x squared y times the sine of z. It's kind of silly, but I mean, in principle, it's possible. Times I hat plus ... So the bx, which is the portion that comes in front of the I hat, it could be a function of x, y, and z in principle. So in order to figure out what the new value at the top here, bx prime, is, I need to know the way in which it changes only in the y direction, actually. And so that's why Ash is right, that down here we need to put del bx, del y. See, it's, again, I want you to compare this to what we said before, which was x prime equal to x initial plus del x del t times dt, right? The thing in the bottom and the top are always going to be the same. Like, these two are going to cancel, basically. I mean, this is a simpler way of saying just, if I want to know what x is at one point, I just take the value of x at another point plus the change in x. Right? Like, 6 equals 3 plus 3. Right? That's really all we're doing. But the change in x itself is the rate at which x changes with respect to time times the change in time, the time interval. And so these dt have the same here, so this dy and dy have to be the same here. I hope that helps you understand it. I don't know if it does. That's okay if it doesn't. We're just trying to get ourselves accustomed to what we're talking about here. It doesn't all have to all make a sense all at once. You can always go back and reread it. I had to reread this stuff several times when I first learned it, and then when I learned it the second time in undergrad, and then when I learned it the third time in grad school, and then when I learned it the fourth time to teach you all. So it's okay to kind of, you're always relearning the stuff to kind of get it figured out. So what's by prime going to be? It's going to be exactly the same, except everywhere there's an x, there's going to be a y. So by prime is going to be by plus the rate at which by is changing. But for by, we're going from here to here, which is the x direction, right? So what I need to know is the rate at which by changes in the x direction, and then multiply that by dx. Again, kind of the dx and the del x kind of cancel here. So we reorganize this a little bit and realize that bx, I'm going to do kind of two operations at once here, so hopefully follow along. Bx minus bx prime is going to be equal to del bx del y dy, except there's going to be a negative sign on here. See if you can follow this step to this step. You should be able to. And the reason why I'm doing that is because bx minus bx prime shows up right here. And then for the other one, over here, we're going to have here. I don't know why I drew that there. I want to kind of separate these two though. Just draw a little line separating what we're doing here. On the right hand side, we just want by prime minus by. So we'll do by prime minus by. And that's just equal to this thing. Del by del x dx. All right, so putting it all back together, plugging this piece right back into here, and going back to our original, what we were saying, if I do the operation of adding up all the b.dls all around this, what I'm going to get, bx minus bx prime is negative del bx, del y dy, but it's also multiplied by dx, plus by this minus this is equal to that thing. So this is del by del x dx from here, and then dy from there. All right, so both of them have dy dx in them, dx dy, but that either one of those could just be the area. The area is equal to dx times dy. Doesn't matter what order you multiply them in, still get the same answer. So on the right-hand side, what we're going to end up having here is, oops. All right, we'll put the one that's positive first. Del by del x minus del bx del y. And then both of those are multiplied by dy dx, which is dA. And that is multiplied, all that together gives us the sum of b.dl. But this piece right here, I'm just going to go back a little bit. So hopefully you recognize this from something we did earlier, although if you don't, I would understand, as we've just been drawing a lot of symbols. But yeah, it's related to the curl. And in particular, it's the z component of the curl. Yeah, cross product. You're right. You're thinking about the right thing, Mr. Miyares, because the cross product and the curl, they're inherently connected to each other. That's okay. Yeah. So, but yeah, Anna said curl, you said cross product, you're both thinking the right thing. Because this piece, if we go back and look, now first of all, if you remember the pattern, it's yx, xy. So this is like the z component, right? So I'm going to write down here what it is. This is like if I took the curl of the vector field B and I just took the z component or the k hat component. That's what that is, right? And that's b.dl. Just to kind of prove that, so we've got del by del x minus del bx del y. You might think, okay, maybe the minus sign's in the wrong position here. Let's check. I can remember that it went x, y, z. That's the order for the first one. The one that's positive is x in the denominator, y in the numerator, and then z. So you should remember x, y, z counting up. And then when it's counting down, you get negative sign. Curl, boom, right there. Del b, so it was del by del x and del bx del y. X, y, yep, there we go. That was the k hat component of the curl, right? So we've now connected this type of operation, right, where we sum over b.dl for an infinitesimal area right here, and that ends up giving us the z component of the curl times dA. Now, in particular, one thing that's interesting about this dA was specifically dx dy. So the curl actually has a direction associated with it. In this case, the direction of that vector would actually be pointing out of the page right here. If it's a positive curl, then this would be the direction of curl of bz. Sorry, the curl of the b, the z component of it, would be coming out of the page right here. So there's this way in which what's happening on the right-hand side is a type of dot product, actually. And well, I'm going to try to go into more detail about this here in a second about how it works, but to give you an idea of where this goes next, what we do is we say, suppose that we don't just do this over a small surface. Now, we did this over a very tiny surface. It was a dA, right? But anything that we can do over a tiny surface, we can make up a larger surface of a bunch of tiny pieces like this, and then do this operation. So the idea would be that if we now were to do this kind of over a more general surface, one that's not necessarily just flat, but could be curved as well, then what would happen is that, so if we kind of just do a sum over a whole kind of, like around the loop on the right-hand side, and then on the right-hand side, we'd be kind of like summing over all the surfaces, so to speak, then what we get on the left-hand side would actually just end up being a surface integral, a line integral around the edge of my surface, and the right-hand side would end up becoming a surface integral over the surface of the curl of b dot dA. This is called Stokes Theorem, I believe. I believe this is called Stokes Theorem. And this applies to any surface where this is the boundary of the surface, the loop is over the boundary, and then this is obviously carried over a surface. Just as an example, a simple example could be, we could do the integral of b.dl around some kind of closed loop, so this would be my loop, or the boundary, and then that would be the surface. And this relates the integral around, the line integral around the outside to the surface integral over the curl of the magnetic field. And of course, this surface can be stretched like a trampoline out and in, and it can be deformed in any way you want. Same thing with the loop, and you can perform this calculation. But Stokes' theorem basically relates the line integral to the surface integral, basically. And the same vector field shows up here, right? That's a pretty powerful idea that we can apply to one of Maxwell's equations, actually, because we have a Maxwell equation that looks like this. It says the line integral of b.dl is equal to mu naught multiplied by conduction current plus mu naught times epsilon naught multiplied by displacement current, which is given by ddt of the electric flux, right? But we can write both of these things in new ways now. The right-hand side of the equation, and we've written it like this before, the current can also be given as a surface integral of j dot dA, where j is the current density, and the other one, mu naught epsilon naught, these just constants, right? ddt, same thing. This can become flux, electric flux is just the same thing as the surface integral of E dot dA. And the left-hand side of the equation, we can use this, which is Stokes Theorem again. We call this Stokes Theorem. We're going to go into more detail about that in a second, but in a way we derived kind of a piece of it, right? We'll talk more about how it all works, I guess. But since we have it, we can apply it to this equation. And this tells us that integral of b dot dl can be written as a surface integral of the curl of b dot dA. Now you might notice that every single one of these is a surface integral on the left-hand side and the right-hand side. And when you have a whole bunch of things that are integrated, not only are they all surface integrals, they're all over the same surface, right? In this case, S is the same in all cases. This is all the same surface. That means each integral is going to have, you might not do it with all the same limits, but effectively they have the same limits of integration. You might find trickier ways to do it over, but they're all the same integral, basically over the same region, right? And that means that we can just equate the integrands. So that means that the curl of B should be equal to mu naught times the current density plus mu naught times epsilon naught times the time rate of change of the electric fields. I believe this one's usually written as a partial derivative too. And in free space, which is something that we investigated with electromagnetic radiation, there are no currents. So that means that the curl of the magnetic field is equal to mu naught times epsilon naught times the time rate of change of the electric field. And that's a really nice equation. It says that if you have an electric field that's changing in time, it produces a magnetic field that's curling, that has a curl to it, right? And we've seen tons of examples of this, right? If I have, I mean, just having current, okay, you can, the current version of this is probably even easier to understand. If you have, let's do the opposite of this. If electric field is not changing, this tells us that mu naught J gives us a curl, right? We know that if you have a current carrying wire, right, that there's going to be a magnetic field that's produced around that's circular, right? And such a magnetic field certainly has a curl to it, right? I mean, it's going in circles. That's a curl. It's a curling field. And that's really what this says, is that having current density produces a curl of a magnetic field. Also, the same thing can be produced if you have a time rating, an electric field that's changing in time. So there we go. This would be, what is this one called? This is the Ampere-Maxwell law. Ampere and Maxwell, because the first half was just Ampere and then Maxwell added in the other part. And again, this is in differential form. Okay, we went through a lot there. Does anyone have any questions? All right, let's do the last one then. So the other equation is integral of b dot dl. Nope, not b. We already did that one. Integral of e dot dl And this one is equal to the time rate of change of flux. So ddt of magnetic flux. But then what we do is we write this one as negative ddt of the surface integral of b dot dA, as many of you had to do on the most recent homework, I believe. And then the left-hand side, integral e dot dl, well, we just saw that we can rewrite this, according to Stokes' theorem, as the surface integral of the curl of the electric field dot dA. And then, again, you make the connection that the integrands have to be the same, so the curl of E has to be equal to negative. I will write this one as a partial derivative, because I think it's supposed to be a partial derivative in all cases. Because in principle, these fields vary with respect to x, y, z, and t. Okay, so you can really see the similarities here between this one and this one now. But that would be Faraday's law. Or Henry's law, whichever one you want to call it, in differential form. And there we go. Anyone have any questions? Or does that all make sense? Those are the differential Maxwell equations. When you put them all four together, they look pretty good. I mean, there's like a lot of similarity to it. So it's, you do divergence of E, divergence of B, curl of E, and then curl of B. See how you're just doing all the operations? You're just going through and checking them all off. These are the only ones you really can do, too. Well, that's not entirely true. You can talk about like the divergence of the curl and stuff like that. We're going to talk about that in a second. But so divergence of E, charge density divided by epsilon naught. Divergence of B, 0. Curl of E, negative del B del T. And curl of B, this is the one that looks a little bit different. Mu naught J plus mu naught epsilon naught. And those are the Maxwell equations. A very nice, succinct way to write them. Probably the least number of lines you can draw because there's not a lot of integral signs hanging out. Which one makes more sense to you and which one you use in a given situation really just depends on what you're doing, I guess. But there we go. Anyone have any questions? Yeah, there's Maxwell's equations. These are the ones that always show up on t-shirts. The thing that says at the front of the... Certainly some of you have seen this before, but at the front of the 1C classroom, it says, and God said, and then it lists the equations, and then it says at the bottom, and then there was light. Which is kind of a joke, but I don't know. I don't know if you think physics jokes are funny. Because the idea, of course, is that, like, you know, this is how light's produced, right? Anyway, it's kind of cheesy, but still anyway. All right. So there's a couple things I want to mention about these vector fields now, and one of them is to look at a particular result from just vector calculus. So in general, if I have a vector field and I perform the following operation, if I take the divergence of the curl of some vector field, does anyone know what this is equal to? So I take the curl of a vector field, and I get some answer, right? And then I take the divergence of the curl. Mr. Miara is right. The answer to this is you get 0. There's a list of a lot of identities like this in your in the appendix C in the lab manual, like toward the end. There's a list of all these different relationships. What's interesting about this is that we know that if we look at this equation right here, the divergence of the magnetic field is 0, right? Oh, I'm sorry. I looked. His name's above your name. Sorry, it was Ash that said the answer was 0. I apologize. All right, so if you look at those two equations, what does that mean? I didn't tell you what the field A was, but if the divergence of any vector field that has a curl is 0, then it must be the case that we can write the magnetic field, perhaps up to some constants, as the curl of another vector field. And you might ask, well, that seems really complicated. Why would we do that? Well, it's really useful, I guess, the best answer I can give you. We call this field A, and A is actually the symbol that's usually used for it. If you want to read more about it, it's called the magnetic vector potential. It has been a while since I studied this, but I will give you some things I remember about it. It's pretty handy in describing things in a lot of different fields in physics. The magnetic vector potential. Is it the same thing as the potential associated with the electric field? That is to say, for the electric field, there's this function that if you take negative gradient of that function, you get the electric field, right? And we call this one just the electric scalar potential field. But we never talked about this, right? We never told you all about a magnetic potential, right? We didn't talk about that, right? So A is kind of the version of that, except instead of being scalar fields, which has just a value at every point in space, this has 3 values at every point in space because it's a vector potential, right? Yeah, so just one thing I will mention about this, though, is this is kind of, to some extent, crucial to understanding. I mean, the big place I remember it showing up in physics, I'll say, is in quantum field theory. When you discuss it, the way that we go about describing some of the symmetries that show up is to say that we can kind of introduce these parameters. You're free to, due to certain what are called transformations. And when you impose all the possible ways that you can transform things, this vector potential equation shows up, and it ends up acting as the photon, which is the kind of particle associated with light. So, I don't know. It's been a really long time since I studied that stuff, and I probably should have looked a little bit of it before we started class today, but just looking at my notes, I remember that I'd written this down, and I wanted to kind of mention it. But yeah, if you're interested, go read more about the magnetic vector potential. It's pretty fascinating, especially if you get really deep into it and learn about how it's connected to photons. Anyway, so there are a couple other things that we want to do here. Really one more thing that we need to do, ideally. And that's to understand more about Stokes Theorem, where it comes from. So we'll do that. We'll talk about Stokes Theorem. So I effectively already used this idea, but we're gonna go ahead and rederive it. So we'll start off with just a normal XYZ plane here. So this is going to be our X, this is going to be our Y, and then Z is going to be coming out of the board right here. And what we're going to do in this is say that we have some loop that we want to perform a loop in a line integral around. So we've got some closed loop like this here. Doesn't like just some random closed loop. Although I'm making it more complicated than I probably need to make it. It just needs to be some closed loop that's not a circle. So that will work just fine. So this is a loop around which we're going to perform a line integral. We'll call the boundary of this loop, we'll just call it C. That's going to be kind of just the boundary. And we want to kind of perform effectively what we did before. What we did was we said we wanted to do the sum of b dot dl. Now we proved before that this gave us a value that was the curl of B. and it was the z component, and that was multiplied by dx times dy. So we're going to use what we did before and say that we can take our object that we have here, and we can break it up into little squares of size dA, or kind of size dy by dx, like this. So we can break our entire surface here up into basically just grid lines, and say that, if I made these big enough, we can always make it bigger if we need to. Say that basically each one of these things has a side here that's dx, and then it's got a side here that's dy. Okay, so dx is this way, dy is that way, right? And then we can say that individually within these loops, we could go through and we could kind of calculate the curl that we get out of every one of them. And for example, let's say that we find the curl around one of these does something like this. And then we look at the next one, and let's say the next one over, just to keep things simple, let's say that it kind of looks kind of similar. But this just means that we're going around the path in this direction here, okay? We're not really worrying about what the individual values of b might be, but what we will notice is that if we make sure that we perform this operation in the same direction every single time, then some things start to become pretty apparent. If we do it in the same direction every single time, always going clockwise, for example, then the adjacent sides will always be opposite to each other. Would you all agree with that? This side on the left and this side on the right, they're at the same point in space. We're just going up in one case and down in the other case. So those two will basically cancel each other out. And we can make that argument at every single point here. No matter what we do, all the ones on the inside are going to cancel out. The ones that won't cancel out will be the ones all the way on the very outside edge. Did that make sense? It's only the ones on the outside edge that are actually going to end up contributing to the total answer of what doing this whole thing over the entire object is going to be. I'll just kind of mix these up a little bit here. This way, this way, this way, this way, that way, this way, this way, this way. Here we go. It's only the external parts that are actually going to contribute. And when we sum up every single one of these over the entire system, then on the left-hand side, we end up doing a loop integral just around the outside. And on the right-hand side, what we end up doing is basically just summing over every single one of the contributions at every single point, right? We're adding up every single one of these over the entire area. And that's how the part on the right-hand side just ends up becoming a surface integral, right? Because you're doing it over the whole surface. And the dot product part comes out of the fact that dx dy is always going to be kind of the surface that's perpendicular to this component right here. And we can generalize this if we want to over any surface. Like we could have a surface that's kind of shaped curvy like this, for example. We can have a surface like this. And our boundary, I don't know if this is going to help if I draw this like this, but now we have a surface that looks like this, let's say. And our boundary C is on the bottom down here now. And now we can generalize this because everything's not just in the xy plane, so that's C. And then the surface is the other thing, the green thing. But the same idea will apply as long as we add up the curls over the surface. They should be related to the circulation around the outside, basically. So that's Stokes' theorem. Explained in a kind of more kind of graphical way. I said I would go into more detail about this, but anyway, that's pretty much it. You have any questions about differential forms of Maxwell's equations and Stokes' theorem and this other vector calculus stuff? You weren't expecting us to... I mean, and I'm sure in your math classes, you guys probably go into a lot more detail on this, but... And I mean, I kind of skipped some of the steps of this, but... I don't know. It's an okay explanation, I guess. It's nothing special. You'll find much more in-depth explanations in textbooks, obviously, including the Physics 1C lab manual, where a lot of this stuff comes from. So. The only other thing I want to talk about tonight's exam, so if we want to move on to that, we can. But if you all want to talk more about some of this stuff, we can. It's more equation-y in Math 220. We have better drawings here. Okay, well. Oh yeah, I mean, I'm immediately remembering all this stuff, like, as I read this, but... Yeah, you can write all of Maxwell's equations. Given this definition of the vector potential, you can rewrite all of Maxwell's equations now, too. In fact, this one right here even changes the scalar potential. You can modify it freely by adding this term. You can put negative del A del T in here. Because if you do this, it won't actually alter the Maxwell's equations. This is called a gauge choice, I believe, or something like this. And, yeah. And that gauge choice we refer to as gauge invariance. And that gauge invariance is what gives rise to the photon. So there's this way in which you can describe how the photon is produced directly from, well, invariance principles, I guess, if you want to say. Again, this is getting into some really technical things, but Ashley's in 220 for me. It was just plug and chug, but here, I like that we talk about it. Okay, sure. Okay, y'all want to talk about the exam then? I thought this would take a lot longer, actually. If I'd known this was only going to take this much time, I would have... All right, so the exam is, you know, the same as before. The one difference is I'm only going to give you lab manual problems now. We have, I don't know, something like 12 to 15 lab manual problems. I'm going to cut them up in parts, basically. Some of them are too long. But so you'll get your problem and about a day before your first exam. So since we meet tonight at 6 p.m., then the first round of people will go... starting tonight, so it'll be like the first half of the class, and you know, you can be kind of sitting in the wings waiting. If you notice there's a spot open, you can always pop in, but I will again give you a schedule with your name as well as the problem that you're going to be doing. Again, I might pull some problems from Mastering Physics if I feel as though they're worthy, and I feel like there's not enough material in the lab manual problems. Maybe some of the lab manual problems I don't feel like are up to snuff. That's the determination I'm going to be making over the next few days. So, yeah, that's basically the idea. We are not meeting Thursday. We're basically just done. So, there's not really anything to meet over on Thursday. Since we're not doing like a full on, like, you know, multiple problem exam, I don't know that doing a review would be particularly useful. We kind of just did a review in a weird way because we kind of reviewed all of what we studied this semester by kind of re-deriving these things. But regardless, that's the other thing, Ash, that I wanted to mention. I have already actually started grading those, and I'll have everything graded before Sunday. You'll have everything back. I started grading this afternoon, and then, as always happens, I got inundated with other tasks from all over the college that I had to take care of, and so I, you know, did that stuff, and then started prepping for class. But actually, not having class Thursday will really help with this, because then I can just make sure I get ahead and do that stuff. So I'll be doing most of this tomorrow, hopefully. I don't foresee myself having any additional work. I think I got everything tied up today, so I'm going to try to finish grading as much as I can tomorrow, and then I should have a few more days. I'm just going to keep going at it. It takes a while. I'm trying to give some feedback. If you haven't already submitted those lab manual problems via Canvas, if you could do that, it's probably the easiest way. That's how I'm grading everything. If your lab manual problem was delivered to me via email or something like that, if you could resubmit it via Canvas, it'll help a lot. It looks like I think most people submitted them via Canvas, from what I can tell. But anyway, there I can just like actually type out the feedback, and then you'll have it directly in your... and some people should have already seen some of that. Some of you in here, I know looking at your names that I already gave some feedback to the first one. Yeah, look, if you're turning them in this week, then whether I get it graded or not is going to be dependent on if you get it to me on time. You know what I mean? So if, like, I'll put it this way. If by Thursday I'm done grading and you turn it in Thursday night, you should have zero expectation that I take the time to go back and look at what you did. So, yeah, I mean, I just, like, if I'm going to actually put the time in and try to get this done for you, you have to do it for me too. You have to get yours in so that I can actually grade it. Otherwise, it's fine. You'll still get credit for it. I'm not really docking significant amounts of points based on when things are turned in. Although I will say, when I noticed that you turned in something that was due in September or October, and it's turned in December, it's definitely not going to look good. You know what I mean? It's certainly going to play into my mental psyche as I'm grading it, meaning I'm probably going to grade it a lot more harshly. But maybe that's good for you. Maybe me grading it more harshly will mean that you get more feedback. I don't know. Who knows? Just saying. It's the reality that it tells me right when I open it in big red letters that it was late, and then that kind of draws my eyes to it. And I can't be unaffected by that, even if I'm not explicitly docking points for it. And I'm not explicitly taking points off for that kind of stuff, but I will probably be a little more. It's impossible for me not to be affected by it. I guess that's all I'm saying. That's pretty much it. Yeah. Can I check the answer of problem 1370 part B because I couldn't get the right one? Yeah, I'll get there eventually. I can pull up problem 1370 right now and I can look at it if you want, and I can talk about the answer. I will say some of the answers in the back aren't right, so, you know. No, I think the answer to that one's right. I'm pretty sure that one's right. For this one, you're doing the average rate. And my recollection is the math is pretty tricky. So, you know, you gotta be really careful about this. But to do the average, you're basically just doing an integral from 0 to TC. And then you're dividing by the period, and then I think the easiest way to do it in this case is because in part A you find the current, part B you're doing it's the rate at which energy is being stored, so it's no, that's not what you want to use, type W, not IRMS. No, you want to use I squared R, I think, if I remember correctly. You want to do I squared R. And you do have to integrate it. You have to integrate it, yeah. But you're doing I squared R for this one. And you're going to integrate from 0 to 2TC. And for TC, you need to use R over L if you want to get everything to work. But if you're careful enough with it, you can get it all to work. Yeah, you're finding the average value of a function with an integral. That's exactly right, Mr. Mears. Yep, that's correct. Now, I will say that in a more direct way to answer your questions, you can ask me about your exam question, yes, before the exam, in a more general sense. I focus more on the second half of your question, which said you're not getting lab manual feedback presently. I am really sorry. Not like it really matters. Apologies suck. It's just, it doesn't matter that I'm sorry about it at all, but I am. It's just, I don't even know if it would have been better if I was in person. I'm always really bad about grading things. I'm just bad about it. But I will get it done. Especially because you're being graded on it, so you need to have some kind of feedback first. But beyond that, once you've gotten your problem, so like, let's see, you'll have your problem on Monday night, right? There's nothing wrong with you trying to contact me between that time and when the exam happens the next night. But just keep in mind that I'll probably put your problem up at, just based on my schedule, it's probably going to go up at like 5 p.m. on Monday night for those of you that are going on Tuesday. And then I have exams from 6 to 9 that night. So then the next day, I will have office hours at 3 o'clock. So that would probably be the best time. If you want to come ask a question about the exam before the exam starts, just come to my office hours. You can email me, of course, but it's just way better if you come to office hours, honestly. If you absolutely can't make the office hours, then, you can go to email and just ask. That's fine, too. I will say the biggest thing I'm noticing from grading people's stuff, just as a piece of advice on the final exam, is you want to make sure you actually have a picture where you define all your variables, and that picture needs to be drawn neatly. That usually means using some type of a straight edge. You've got pen and paper that you can do this on, of course. Just those pictures are just as important as the math. Like, I'm genuinely or generally assuming that given enough time you could figure the math out. But if you don't have a picture to go along with it, then I start to question whether you understand it, I guess. It's the simplest way to put it, I guess. So just that's something to work on when you're writing your problems up, is just to make sure you've got a nice, clear picture. When it's relevant. That's not all the problems have pictures in them, So Tuesday at 3 p.m., that's right. I also have office hours from noon to 1. So on Monday. No. 1 to 2 on Monday, right? Yeah. Monday is 1 to 2. All this information's in the syllabus. But sitting here talking to you with this blank screen is kind of boring. But Tuesday at 3 p.m., yeah. And in general, I'll be around most of the day Tuesday anyway, so if you want to come talk to me. I probably will. This is next week, right? Yeah, I won't be there right at 3 p.m. Yeah, I definitely have a meeting at 2:30 next week. So actually, it's going to be a little later. The last week, the meeting was only 15 minutes. But the 2 weeks before that, the meeting was an hour and a half. So hopefully it's not too long next week. It's finals week. I don't think they're going to keep us there for too long of a time. I think it should hopefully be pretty quick. We're just doing some course reviews. But Tuesday afternoon, definitely before the exam, you will have some time to come talk to me if you want to. For sure. And if there's anything you're confused about during the exam, you can ask at that time too. And I know these problems are hard, but you all can do them. I mean, looking at your work, No, so Kiana, to be more clear, it's I'll type it real quick so it's really obvious. There we go. There we go. So it's everything, basically, Keanu. It's basically everything. So really, what you'd want to review is you'd want to review your lab manual problems. And I'll try to get them graded within the next few days. I think I can get most of it graded tomorrow. I was able to go pretty quickly through it today. The thing that's kind of time-consuming is typing up advice, but yeah. I mean, I can stick around and I can talk to you until class ends, sure. Yeah. I will go ahead and stop the recording. I don't want it to get too long. It's already hitting close to an hour, and I think over an hour is kind of too long. So stopping recording.